Welcome back, folks. Today we're focusing on the more complex solutions for the more complex vector questions. In this particular video, we're going to specifically look at vector equations that don't make triangles directly, or vector equations that do make triangles, but the triangles themselves aren't right angle triangles. They're scalene triangles and a little bit more involved with them. Let's take a look at an example of the first type where we actually have a shape that's not going to make a triangle. In this example, we're looking for the resultant of vector A, which is 10 meters north, plus vector B, which is 50 meters west, vector C, 20 meters south, and vector D, which is 30 meters east. So in this case, we are definitely not going to get a right angle triangle, or at least not one straight away. So this first method we refer to as basically a geometric perspective. And with this one, essentially you sketch out the diagram and you sort of suss out the triangle to solve what you need to solve based on the shape. In this case, it's fairly straightforward because all the vectors are playing nicely, which means they're either all on the y-axis or on the x-axis, nothing weird in between. So we take a look at vector A, and if you recall, we always start from the tail of A, and then A attaches to, the head of A attaches to the base of B, and then the head of B attaches to the tail of C, and the head of C attaches to the tail of D, and then finally, that is our end point. So our resultant always starts from the tail of A to the head of our last vector, which in this case is vector D. And as a reminder, I prefer to have the resultant dashed. Now the next trick is we have to generate a triangle out of this in order to be able to solve for R. And it's reasonably obvious where that triangle is. But let me give you a little idea of how we come up with that. So you can see already we have this value on this part is 10 and this part is 15. And what I mean by that is as follows. That resultant actually has two parts. That resultant has a part that goes along the y-axis, this component right here, and then another part that goes along the x-axis right there. So we know that we're going south then east, but if we look at the way it's drawn, we go south, then we go east. Now, how do we come up with these values? Well, that value 10 is fairly obvious because if this side, A, is 10 and all of side C is 20, obviously the remainder here has to be 10 as well. And then the same thing goes for this value 15. We know that the length of this side is 15 and the whole length of this side is 30. That means the remaining bit also has to be 15. So really, with a problem that is of this complexity, it's fairly easy to get those values just by inspecting the diagram. There are obviously going to be questions where it's not this easy, but we'll get to that. So now we can see that we have a part that goes along the Y, and we actually have a name for it. And this little part here is actually called your RY. Essentially, the Y component or the Y part of our resultant. And then this part along the x-axis, we call Rx. To say it another way, this resultant could also be achieved by taking this path and then that path. They're equivalent. Obviously, the resultant R is the most direct approach. So based on this and realizing that our vectors are along the x and y axis, we know that this is a right angle triangle. So we can find the magnitude of R just using Pythagorean theorem. So that's your x squared plus your y squared. So just so that we're clear, what I'm referring to by my x is the magnitude of that vector there, and what I'm referring to my y is the magnitude of this vector over here. A quick calculation will show that the magnitude of R is approximately 18. Next, finding theta. As I mentioned earlier, we try to avoid using found values, so you want to avoid using the R if you can. In this case, we can do that, and the reason being is because this value 15 and this value 10 came from the given values, and there's no rounding issue with this whatsoever, where this value of 18, there was rounding involved. Since theta is over here, this is our opposite side, and then this one is the adjacent. So the opposite is 15, the adjacent is 10, we get an angle of 56 degrees, therefore the resultant is equal to south 56 degrees east. And again, let's talk about how we get that south 56 degrees east. it's always good to go back to where we started, vector A, tail of vector A. So what I'm going to do here is I'm going to follow my triangle, and initially we're pointing south right now. Then I have to drift or turn towards the east, and I turn by the equivalent of that angle theta, which is 56 degrees. So we have south, 56 degrees towards the east, and that's how we get that direction. Method 2. Here we're going to solve it directly from the mathematical perspective, which means that you're not going to actually rely on just inspecting the diagram itself. And the reason why we want to do it the mathematical way is because sometimes we're going to have more than 4 vectors. And by having a more rigorous mathematical method, it makes future problems a little easier to work with. So we have the same diagram as we did before. But as you can see, I've drawn a separate diagram down here that shows what I discussed earlier, that y component of the resultant and that x component of the resultant. So the next step, what we're going to do is we're going to find the magnitude of our resultant. What I did here is I actually took our original equation, which is r is equal to a plus b plus c plus d, and I rearranged the order because, as you recall, the order does not matter. The order in which you do vector addition does not matter. So I grouped them. I grouped them together in terms of the axes, I should say, that they lie on. So vectors b and d, they're along the x-axis, where vectors a and c, they're along the y-axis. So I then separate the equation. I separate it into the x component and the y component. So now when we look at the x component, and that's where we get the rx, that's just equal to vector b and vector d. The advantage of doing it this way is then we can actually use plus and minuses, right, positives and negatives, to represent direction. So vector b was 15 meters to the west, therefore negative, where vector d was 30 meters to the east, therefore positive. As a result, Rx is equal to positive 15, or 15 meters to the east. And if anyone notices, I forgot to put in my plus sign there. 15 meters to the east. Okay, apply the same thing to the y component. So Ry, or the component of the resultant that falls along the y-axis, is equal to vector A plus vector C. Now vector A is going north, so that should be positive, where vector C is going south, and that makes it negative. The result is negative 10, or 10 meters south. And again, we do the exact same thing. Now, the beauty about this explains why this arrow goes down, and this explains why this arrow goes to the right, or to the east, rather. And then, of course, using Pythagorean theorem as before, and then using tangent to find that angle, we get the same answer as we did before. But as I mentioned earlier, they're not always that easy. Let's take a look at this example over here. In this example, we want to find the resultant of vector A plus vector B. But vector A is going 20 kilometers north 45 degrees east, where vector B is 10 kilometers east 30 degrees south. Neither of those two vectors are playing nicely. So to solve this one, we really need to rely heavily on drawing an accurate scale diagram. I want to qualify that. When I say an accurate scale diagram, we're still going to solve it mathematically, which means that you don't have to get it down to the fraction of a decimal in terms of the lengths and the angles correct, but they really do have to be close. And what I mean by that is you need to be able to sort of think through the numbers a little bit. Like, for instance, take a look at vector A. It has a magnitude of 20, where vector B has a magnitude of 10. On your diagram, that needs to be reflected. Vector B has to be half the length of vector A. So it needs to be fairly obvious. You can't draw them the same length, that's for sure. And we do the same thing with the angles. Like, I'm not expecting you to use a protractor, but when you draw this angle here, it's got to be 45. This angle here is 30. So it can't look like a 45 degree angle. So you have to have some care in the way that you draw these diagrams if you wish to solve these successfully. We're going to start off by taking a look at the diagram. So the first thing you always start off with is you got to start off with your compass rose. So we have our compass rose there, and then we go with the vectors themselves. So let's take a look at the first vector. Now we know vector A, and we'll choose a different color. We'll use blue this time, I guess. So we know that vector A is north 45 degrees east. So we start off, so let's say this is our vector A. We're pointing north, and now we're going to rotate 45 degrees towards the east. And there is our vector A. Next step, we draw another compass rose where these two vectors connect. So now we have to draw vector B. And this time I'll make vector B green. So again, looking at what vector B is, we know that it's 10 kilometers, so it's half the length of vector A. And we start east, and then we rotate 30 degrees towards the south. So we point east first, then we rotate 30 degrees towards the south, and there is my vector B. And that means that this angle here is 30 degrees. That's not inside the triangle that we want. That 30 degrees is outside. So that being said, we need an internal angle because we have the magnitudes of these sides. So we know that side B has a magnitude of 10, side A has a magnitude of 20, but what we need is an internal angle. And we're referring to this angle here. That's our internal angle, which we are going to call angle R. And the reason why? Because that is opposite of the resultant. So in order to get this angle inside here, we have to figure out a couple of things. First of all, let's take a look at this angle gamma. Now, we know that that is 45 degrees. How we know that's 45 degrees has to do with the Z pattern. And in case you're unclear what I mean by the Z pattern, let me literally highlight it for you. There's the Z pattern right there. Maybe I'll highlight it even more intensely. There, there, and there. This angle and that angle. There's your Z pattern. So we know that gamma is going to be 45 degrees. Next, let's focus on this angle alpha. Alpha is going to be 60 degrees. And the reason why it's going to be 60 degrees is because of complementary angles. Remember, this whole angle here is 90 degrees. So going from east to south, that total is 90 degrees. This part is 30. Therefore, the remainder, which is alpha, is going to be 60 degrees. Then finally, to find the the angle R, to find angle R, that's just going to be the sum of alpha plus gamma, which is 105 degrees. So now what we have is side, angle, side. So that will be cosine law. So let's try to get everything relevant inside the diagram here. So when we take a look at this diagram, what we're trying to find is the resultant. So we have to use cosine law in that form where we're looking for the resultant. That's why it is r squared is equal to a squared plus b squared minus 2a times b cosine of the angle r. Some of you might be scratching your head a bit because it doesn't look exactly like what you remember cosine law to be. Don't panic. Cosine law is just a general formula where it's in this form. C squared is equal to a squared plus b squared minus 2ab cos of angle C. All I did is replace C with R. Doesn't really matter. The names are all the same. All right, so substituting in, sorry. We don't substitute in yet. We isolate for R. Now, I also want you to note something. The first line, I have it in the full vector notation. And when you see this, remember, that means the magnitude of vector R, the magnitude of vector A, the magnitude of vector B. But you can, after you write out this line the first time with the more complex notation, you can then just write it R by itself without the harpoon. That means magnitude as well. This is technically a more precise way of just saying it, but it does take more time to write it out. All right, so isolating for R, I take the square root of both sides. So that's the square root of a squared plus b squared minus 2ab cos angle R. Substituting these values in, we get 24.6 kilometers. Next, we have to find our direction. This is where things get interesting. We're going to zoom in again. And I want you to notice something. Look where I put my theta. The theta is not inside our triangle. And let me explain. Theta always needs to be referenced against one of the points of the compass rose. So, for instance, north, east, south, and west. What you're going to see is that our resultant falls somewhere between the north line and the east line. So when you draw your vector R, there's actually two ways you could do it. You could start from the east and move north, or you could start from the north and move east, which means that we could actually find this angle instead. So the question is, why did I choose this one here? And to be honest with you, the only reason why I chose that is because it's less clutter in the diagram. Otherwise, I'd have to draw my theta like that, and that just makes things look more cluttered. It's fine, it's also correct, but this looks a little prettier to me. So here's the next argument. I want to find theta. Now, in order for me to find theta, I need to know some information. First of all, between north and east is 90 degrees. So that means that theta plus this angle B here, and it's angle B because it's opposite side B, plus this 45 degrees, those have to add up to 90 degrees. So theta plus angle B plus 45 is equal to 90 degrees. Now I want to talk about this though. See this 45? That's a measured quantity and that is good to 3 sig figs. But this 90, that 90 is actually exactly 90, which means that it has infinite precision. We just don't bother writing all the zeros. So that technically is 90.000000000. Wait literally forever. 0.0000000. Keep waiting. You get the idea. There are actually no limits to the number of decimal points. So when you're actually talking about in terms of significant figures, things like values like 90 degrees, like right angle, we know that these two vectors are perpendicular to each other. That is by definition an exact number, unlike this 45, which is an actual measurement. It could be 45 point something. Anyway, we get the idea. So in order for us to be able to solve for theta, we have to find angle B first. So let's do that. Now, here's the deal. We have side A, side B, and now we have side R. However, we only have angle R. So if we want angle B, we have to use sine law in this case. So the version of sine law we're going to be using is the sine of angle B over side B is equal to the sine of angle R over R. And my angle symbol is literally terrible. And also, I don't know the difference between upper and lowercase apparently. So this is how we're going to solve for good old angle B. Let's do it. So again, finding angle B using sine law. As I've mentioned several times before, I want you to isolate for the vector first. For the angle first, and then put in the math. And of course, hilariously, I did not follow my own policy because I went with the sine, and I should have actually isolated for sine first before I put these numbers in. I guess I'll have to revise this note a little bit later. But in any case, I digress. So we isolate for B. Oh my goodness, look at all these mistakes. That shouldn't be there. All right, so what we've got is angle B is equal to the arc sine or sine inverse of 10 sine 105 or 24.6. So we get angle B is equal to 23.1. And now we can find our theta. So 45 plus angle B plus theta is equal to 90 degrees. Our theta is 21.9 degrees. So therefore, our resultant is 24.6 kilometers east, 21.9 degrees north. Okay, so here are the 2 questions for homework. Give these ones a shot, and I will post the solutions as a video tutorial in the next 2 videos. Or actually, more realistically, in the next single video.